geometrical optics. When we talk about the optics, we just mainly consider the visible light. Okay, it means that the wavelength of the electromagnetic wave is just about the 300 nanometer to about the 750 nanometer, starting from the blue light and then to the red light. We can categorize the optics into the two types. The first one is called the geometrical optics, and the second one is called the physical optics. The geometrical optics, right, it's going to be the case that the wavelength of the visible light is much less than the size of the device. Okay, for example, the wavelength of the visible light is just about the 350 nanometer to the 750 nanometer, right? And then if we consider a mirror on the lens, okay, so now you can see that the size of the mirror and the lens, right, just much larger than the size of the wavelength. Okay, so that's going to be the geometrical optics. But then on the other hand, for the physical optics here, the wavelength of the visible light must be greater than the size of the device. Okay, so for the physical optics here, we will talk about we're going to talk about the properties of the physical optics later in the next chapter. But now in this chapter, we just want to talk about the geometrical optics, right? So we want to consider the refraction of the visible light on an interface. Okay, and we need to know about the Snell's law and the total refraction. So I think these topics you have learned a lot from high school, so I'm gonna go quite fast here. And then later on we talk about how the image can be formed. Okay, so we have this device to form the image. So we have the planar mirror, we have the spherical mirror, we have the imaging by the refraction, so this will be the new things for you, and we have the thick sense, so this will be the new thing for you as well. Okay, and then finally we have the thin sense, and then later on we can have the combinations of this device together. Okay, so when we talk about the refraction and refraction, right, we just use the light ray. Okay, we just use the light ray to represent the direction of the visible light. For example, if we have a point source here, okay, if we have the point source here, and we know that the point source, right, it will radiate the electromagnetic wave in all directions. So this cross section, right, is gonna represent the wavefront of the expanding wave. Okay, so this we call the wavefront. Okay, so what is the wavefront, right? So the wavefront is just going to be the wavefront here is just going to be the crest. Okay, it's going to be the crest of the wave. It's going to show the position of the crest of the wave here. Okay, and then also we can just write down the light ray, right, to be an arrow pointing from the wavefront, pointing from the source here. Okay, pointing from the source to direction of the wavefront. Okay, so this will be direction of the light ray. Okay, so if you look at the 2D picture here, right, it just looks something like this. So when you have the source here, and then you have the wavefront, so don't forget that the wavefront is going to be the position, right, of the crest of the wave. And then we can have the light rays to be represented as the arrow, right, coming from the source and into the direction of the propagation of the wave. And here's with another case here. Okay, so one thing that you can notice from these pictures is that, okay, the distance from the wavefront to another wavefront, right, is going to be the wavelength of the electromagnetic wave. Okay, the distance from the wavefront to another wavefront is the wavelength of the electromagnetic wave here, because the position of the wavefront is going to be the crest. Okay, so if you look at the psi graph, right? Okay. Okay, if you look at the psi graph here, so it means that the distance from the crest to the crest is just equal to one wavelength lambda. Okay. One more thing, direction of the light rays must be perpendicular to the wavefront, for example here. Okay, or for example here. So this you need to remember this property. So we said that the light ray must be perpendicular to the wavefront. Alright, okay. So now you know about the light rays already. Then we can use this light ray to study the property of the refraction and the refraction of the electromagnetic wave. So let's consider this picture. Okay. So now we have the light, okay, coming from the medium 1 and then transmitted to the medium 2. So let's say that the refractive index of the medium 1 equal to the N1 and refractive index of the medium 2 equal to the N2 here, right? So it means that, from the previous chapter, right? So we say that the speed of the light must be different, okay? Because we have this relationship, we have the V equal to the C and then over the N, right? Where the C here is with the speed of the light in the vacuum, and the N will just represent the refractive index of the medium. So it means that the speed of the light in that medium will be changed, just depending on the N here. Okay. And also we know that from the V equal to the frequency times the wavelength, right? So now in this case, don't forget that when we have the light coming from one medium to another medium, the frequency, okay, so this frequency remains constant, right? The frequency remains constant. Why? Because frequency always depends on the source, okay? Because that's only related to the source. Okay, it's just depending on the source only. So that's why when we have the electromagnetic wave propagating from one medium to another medium, the frequency must be the same. Okay, so now if the frequency is the same, but we know that the speed of the electromagnetic wave is changed, right? It means that the wavelength will be changed as well. Okay, so when we combine these two equations together, okay, so let's just consider the first equation. From the first equation here, we have the N is inversely proportional to V, right? Because V equal to the C over N, so this N equal to C over the V, right? So the N is inversely proportional to the V. But we know that the V is proportional to the wavelength, okay? So it means that this N, right, is going to be inversely proportional to it's inversely proportional to the wavelength as well. Okay, it means that if the N is large, the wavelength of the light will be small. If the N is small, so the wavelength is be large. Okay, so now from this picture, right, this is the normal incidence. It means that if we just draw the light ray, so the light here, right, it just incident normally to this interface, okay, to this interface here, and then the light, some part of the light will be to the medium 1, and some part of the light will be refracted into the medium 2. Okay, so let's consider the wavelength. So now from the medium 1, right, the wavelength of the electromagnetic wave is just equal to the lambda 1, which is larger than the wavelength of the light in the medium 2. Okay, so now you can see that in this case, right, the lambda 1 is greater than the lambda 2. So if the lambda is large, it means that the n is going to be small. Okay, then we can have that then the n1 should be less than the n2. Okay, so it means that we can have the light coming from the less refractive index to the high refractive index here. For example, it can be from the air to the glass, right? Because index of the air just equal to 1 and the glass equal to the 1.5. Remember from the previous chapter here. Okay, so what happens if we have the oblique incidence? Okay, sorry. This is the normal incidence, right? But then if we have the oblique incidence, the oblique incidence means the light will make some angles to this line. Okay, so this is called the normal line. So the word normal in this meaning, right, it just means the perpendicular to the interface. Okay, so it will be a line, a virtual line, which is perpendicular to this interface here. Okay, so that's called the normal line. Then we have the incident light, okay, coming from this direction and then hit at this point on the interface, right? So then that's why we can just draw the normal line here. Okay, and then some parts of the light will be reflected to the air, and then some parts of the light will be refracted into this so this picture we use the water, right? But let's say that, okay, get the water, so some parts will be reflected into the water here. Okay, so then we call this ray as the incident ray, and the reflected one is called the reflected ray, and this ray is just called the refracted ray. Okay, and we can define the angles. We can define the theta 1 here, right, to be the angles of the incidence, to be the angle of the incidence theta 1. Okay, so now the theta 1 palm is called the angle of the reflection. Okay, the angle of the reflection here. And then theta 2 is called the angle of the refraction. Okay, so one thing that you need to keep in mind is that the theta 1 palm, and theta 2, right, is to be the angles that the light rays, okay, making with the normal line. Okay, so you need to be careful with this one. Theta 1 palm, theta 2 is to be the angles that the light ray here making with the normal line. Okay, so it's not this angle, and it's not this angle, it's not this angle, so just be careful. We can use Maxwell equation. Okay, remember from the previous chapter, we can use Maxwell equations and the boundary conditions that we haven't mentioned before. Okay, we can use the Maxwell equation and the boundary conditions to solve the relationship between the theta 1 palm, and the theta 2. So this is called the law of refraction and the law of the refraction. Okay, for the law of refraction, we can show that the theta 1 equal to theta 1 palm. So it means that the angle of the incidence is just equal to the angles of the reflection. So that's called the law of the refraction. Again, the law of the refraction, right, or just called the Snell's law. Okay, it is the n1 times the sine theta 1 equal to the n2 times the sine theta 2. The n1 and the n2 is going to be the refractive index of the medium 1 and the medium 2 respectively. Okay, the theta 1 and theta 2 or the angle of the incidence and the angles of the refraction respectively as well. Okay, so let's consider this picture. Okay, if the refractive index, right, of the medium 1 and the medium 2 are the same, so on the other hand, it's just the same medium. Okay, so now you can see that if the n1 and the n2 are the same, so it means that the theta 1 must be equal to the theta 2, right? So that's why you can see that when we have this incident right here, okay, making the angle theta 1, so now the refracted light, okay, it's not gonna bend. Okay, it's not gonna bend. It just we have the same direction as the incident light. Okay, so this angle must be the same, theta 1 equal to the theta 2. Now, okay, picture B, right? If we have the light propagating from from medium 1 to the medium 2, but now in this case, if the n1 is less than the n2, right, it means that the medium 1, okay, the medium 1 here is going to be the less dense. Oops, sorry, because the n is less, so it means that dense is be less. And now the medium 2, right, so let's say that okay, so now we know that the speed of the medium 1, right, if the n is smaller, so it means that the speed of the medium 1 will be higher. Okay, so in this case, if we have the higher speed, and now for the medium 2, right, because the n is larger, it means that the speed of the light will be lower. Okay, so this will be the lower speed here. Okay, so now we say that if the speed is higher, so it means that the wavelength will be higher as well. Okay, if the speed is higher, so the wavelength is going to be the higher as well. Then from this picture, right, okay, so let's draw the wavelength in this case. Okay, so this kind of represents the wavefront of the electromagnetic wave. Okay, so let me just show the wavefront here. Okay, this will be the wavefront of the incident light ray. Okay, so don't forget that the wavefront must be perpendicular to the light ray, right? And then okay, something like this. Oops. Okay, so now for the refracted light, okay, we just draw the wavefront as well. So don't forget that the wavefront must be perpendicular to the light ray, so it's gonna look like this one. Of this, right? Okay, so one thing that you can notice that, okay, if this distance, right, is going to be the wavelength of the light in the medium 1, let's say the lambda 1, and now this and then here is going to be the wavelength of the light in the medium 2, so let's say the lambda 2, right? So it's clearly seen that the lambda 1 is greater than the lambda 2. Okay, so as we just expect, right? Okay, and it means that this refracted light must be bent toward, okay, bent toward the normal line here. Okay, so let's mark this one. So the ray is bent towards the normal line. Okay, so now remember that if the light coming from the lower index to the high index, right? So the light ray of the reflected wave will be bending towards the normal line. Okay, and that's it. But now on the other hand, if the light ray, right, just coming from the higher dense to the less dense. Let me change this. Let's say the higher dense. Okay, so we have the N1, right, which is denser, and less dense, okay, for the N2. It means that the speed of the light in the medium 1, right, should be less than the speed of the light in the medium 2 here. So here we have the lower speed, and here we have the higher speed. Okay, we have the high speed here. Okay, then again it means that the wavelength of the light in the medium 1 should be less than the wavelength of the light in the medium 2. So then finally we can see that the refracted light, okay, so this one is going to bend away from the normal line. Okay, so let's mark this. The ray is bent away from the normal line. Actually, this can be seen from this equation as well. Okay, so let's consider in this case. So you can see that if okay, if the N1 is small, right? In this case, if the N1 is small and if the N2 is large, so it means that the theta 1 must be greater than the theta 2. Okay, so that's why in this picture the theta 1 is greater than the theta 2. But then on the hand, in this case, if the N1 is larger than the N2, okay, so the theta 1 should be less than the theta 2. So that's why in this picture you can see that the theta 1 is less than the theta 2 here. Okay. Okay. So now let's consider this picture. We have the light source here. Okay. So the light source is inside, let's say, water. Okay. And this is going to be the air. Okay. So let's say that this will be the water. Oops. And here is going to be the air, right? And then this line is going to be the interface between the water and the air. Okay. This light ray, right? You can see that the incident angle is quite small, right? So then we can have the reflected light. But then if we increase the incident angle more and more, at some point all the light will be reflected back to the water. Okay, so this behavior is called the total internal refraction. Okay, the total internal refraction. Okay, here. The total internal refraction occurs when we have the light ray, right, coming from the higher dense to the less dense. Okay, so let me just mark here. So from the large n to the small n. Okay, for example, from the water to the air, right? Because reflecting index of the water just about 1.5 and the air just about 1. So the 1.5 is greater than 1. Okay, so we can have the total internal refraction. Okay, so now we say that Okay, so let's say here, if we have this incident ray, right, and we know that some parts of the ray, okay, is going to be reflected in the medium 2 in this case. Okay, so don't forget that. When we have the light coming from the higher dense to the less dense, so the reflected ray must be bent away from the normal line. Okay, but then what happens if we increase the angle of the incidence? Okay, so let's consider maybe this one. Okay, if we increase the angle of the incident, okay, so now this reflected ray, right, is going to be bent away more from the normal line. Then it's possible that this reflected ray will make the 90 angles to the normal line here. Okay, it can make the 90 angle to the normal line. Okay, but then what if we increase the incident angle more? So now you can see that we will not have the reflected ray anymore, but then all the lights will be bent, will be reflected from this interface. Okay, so this can be occur in this case. Okay, so this phenomena is just called the total internal reflection. Okay, so it's with the reflection of the incident ray and then go back to in this medium again. Okay, now we can define the angle. So let's say that we can define this angle, this incident angle, that's making the angle of the refraction, right, equal to the 90 degree here. So let's call this incident angle to be, okay, let's call this angle to be the critical angle. Okay, so let me use symbol as the theta c for the critical. Okay, so we can say that at the critical angle, so the angles of the refraction equal to the 90 degree. Okay, the angle of the refraction is 90 degree. So now we need to find an equation that we can use to find these critical angles in the terms of the n1 and the n2. Okay, so let's just start from the Snell's law. Okay, let's just start from the Snell's law, all the laws of the refraction, right? The Snell's law say that the n1 times the psi theta 1 equal to the n2 times the psi theta 2. Okay, so the theta 1 is with the incident angle and theta 2 is with the refracted angle. So now in this case, the theta 1 equal to the theta c, the critical angle. Okay, so we have the n1 times the psi theta c equal to the n2. So now for the theta 2, right, the refracted angle equal to 90 degree. Okay, and we know that the sine 90 degree equal to what? Equal to the 1, right? Equal to the 1. So then here, finally, we can get that the sine of the theta c, right, is going to be equal to the n2 and then over the n1. Okay, so this can be the equation that we can use to solve for the critical angle, the theta c. So it means that if we know reflective index of the medium 1 and medium 2, then we can just solve for the critical angle on this interface here. Okay, and one thing that we can notice from this equation is that because we know that the sine theta c, right, must be less than 1. Okay, so that's the property of the sine. The sine function must be less than 1. So to use this equation, it means that the n1 must be greater than the n2. Okay, the n1 must be greater than the n2. It means that the light must come from the higher index and then to the lower index here. Okay, so don't forget that. Okay, one more thing that we can get from this question. So now this theta c, right, the critical angle, so it should be the angle of the refraction equal to the 90 degree here. Then if we want to have the total internal reflection, it means that the theta 1, right, which is the incident angle, okay, the theta 1 is the incident angle, must be greater than the critical angle. Okay, so that's going to be the condition that we can have for the total internal refraction. Okay, so for example, in this case, right, in this case, so in this case, you can see that the theta 1 here will be greater than the critical angle. Okay, let me, okay, I'll just write down. So this will be the normal line, right? And then this angle, the theta 1 is greater than the critical angle. So if you have, it just encounter the total internal refraction. Okay, so let's look at the examples.